Let's start with the example of a non-uniform rod. Now we all know that if you have a uniform rod, the center of mass is going to be at exactly halfway point. So there is no fun doing it. Now how can we take a non-uniform rod here in physics? There are two ways in which we can define a non-uniform rod. One is to have a rod whose area of cross section is constant. So let me take a rod whose area of cross section happens to be a constant like this. But this rod's linear density keeps on changing as you move across the rod. So maybe the material becomes denser and denser and denser as you move towards right, or it becomes rarer and rarer and rarer as you move towards right. That can be achieved by making a composite rod, a rod of 3 or 4 different materials. So maybe a small piece of copper, then a small piece of maybe iron, then a small piece of something else, and so on. So you can make a non-uniform rod of uniform cross section, where what we have to vary is the linear mass density, the mass per unit length. So if I take a unit length on the left hand side and if I take a unit length on the right hand side, their masses will be unequal. That will be intrinsically because of the difference in the materials that I have taken. There can be another kind of rod, non-uniform rod, which is more like a baseball bat. So what happens for that kind of a rod is, you have got the same material throughout. So a baseball bat is probably made out of the same piece of wood or the same piece of metal, but it is increasing in thickness. It's like the club that we used to hunt animals long back, So something of this kind. This is again a non-uniform rod. So there can be two different kinds of non-uniform rods, and let us deal with them. Let us first take the first kind, where the area of cross section is a constant, but the linear mass density varies. So let's say, let me take that rod, people, somewhere here. Yeah, so this is the rod that I have chosen, and maybe I have got lambda is equal to ax plus b, let us say, or a plus bx, easier one, no, it's the same thing. So a plus bx, let us say. This is how lambda varies, where x is the distance from the left end. And we are supposed to find out the center of mass of this particular rod. So since it's a rod, it's a one-dimensional object, I can take x-axis along the rod itself. So there is x-axis along the rod, and I can also take the left end as the origin. So I'm going to do that. The rod is put here. This is the rod. There is x-axis that runs along the rod like this, and the leftmost end of the rod is x is equal to 0. So if the rod has got a total length L, so let me give you that variable, length of rod is L. So the rightmost end has a x coordinate, x is equal to L. And I need to figure out the center of mass. So what I'm going to do is, because it's an extended object, I'm going to chop it up into small pieces. There is maybe a small piece somewhere here that I'm interested in. So that blue shaded piece is what I'm interested in. Now for this blue shaded piece, I need to find out two things. One, I need to find out how much is its mass. And second, I need to find out what is its x coordinate. Only then I will be able to frame that integral x dm and then integral dm. So how can I define its mass? Its mass will be defined in terms of its length. But how can I define its length? So for that, since I'm taking a small length, probably I will use dx. But dx is a change in x, so I'll have to define x. So maybe this element is at a distance x from the left end. So let's say that there is this blue element which is at a distance x from the left end, and the length of this element itself is dx. And that will help me to figure out its mass. So therefore, its mass is equal to mass per unit length, that is lambda, times its own length, which is dx, which I can say is a plus bx into dx. And those who don't want to do it like this, they can do it in a slightly different way. they can say that if this element has a mass dm, if the element has a mass dm and length dx, then its lambda can be written as its mass divided by its length, and lambda at a distance x from the left end will become a plus bx, and that will again give you the very same equation that we have got earlier. So the mass of this element is known, a plus bx into dx. Its x coordinate is also known. So therefore in the center of mass formula, in the center of mass formula, the numerator term is integral of x dm, which will turn out to be integral of x times a plus bx dx. And I will have to find out this integral, and what are the limits that I take. The limits for this integration will be always from the least value of x to the largest value of x, because here the variable of integration is x. So the least possible value of x is 0 when I am taking the element at the leftmost end, and the largest value of x is L when I am taking an element at the rightmost end. So the limits will be 0 to L, and I will insert the limits here, 0 to capital L, and my integration will give me ax square by 2 plus bx cube by 3 going from 0 to L, which will be al square by 2 plus bl cube by 3. This is the numerator. And what about the denominator? So when I try to find out the denominator, let me do it here itself. Let me just shift these guys. Yeah, fine, works. So I can find out the denominator here itself on the right hand side, and I can say denominator will be just integral of dm. So that will be integral of a plus bx times dx, where the limits of x will be again from 0 to L, and after you integrate you are going to get al plus bl square by 2. You should integrate and put the limits and you will get this end result. That is trivial. And now you can figure out the total mass. The total mass is this. So if they ever ask you to find out the total mass of this rod, you have this answer here. Total mass of the rod. And if you have to find out the center of mass, then x center of mass will be al square by 2 plus bl cube by 3 divided by al plus bl square by 2, wherein I think you can take the LCMs and do something, and your answer will be 3al square plus 2bl cube divided by 6. This is the numerator, divided by 2al plus bl square divided by 2. That's the denominator, and which will eventually give you here, this will flip over, so 1 by 3 of, and maybe 1l will cancel out, so you will have 3al plus 2bl square divided by 2a plus bl. This is the final result that you are going to get. Now, does that result make sense? So a good practice is, after you have got an answer, you should check it against some known or expected cases. So one expected case is when lambda is a constant. So you have a rod of uniform cross section where the linear mass density also is a constant. Then if lambda is a constant, then we expect the center of mass to be at the center, so L by 2. So this formula should break down to L by 2 if I put lambda as constant, and for lambda to be constant, B should be 0. Only then the variation with respect to x will be removed from this particular equation. So case 1, lambda is constant, it implies that B is 0. So therefore X center of mass then becomes, and the formula was this formula. You can insert this formula here with B is equal to 0. So the moment you say B is 0, that's gone. The last two terms in the numerator as well as the denominator are gone. 1 by 3 of 3AL by 2A. 1 by 3 of 3AL by 2A. And you can throw away the 3's and the A's and you will get L by 2. Done. So yes, this formula checks out against a known result. And then let's take an interesting result. Sometimes they say that lambda is a linear function. Of course, this was also a linear function, but they say that lambda is proportional to the distance from the left end. You will have to keep in mind that this is not exact proportionality. This is linear but not proportional. So when they say it is proportional, when lambda is proportional to x, then maybe lambda is equal to some lambda naught times x, where lambda naught is the constant of proportionality, then a is 0. So when I have this case, a is 0 and b is lambda naught. So let me put that in my result here. So the moment I put a is equal to 0, you see that in this result, if I put a is equal to 0, the first term will be gone in both the numerator as well as the denominator. And when I put b as lambda naught, I am going to get, therefore X center of mass will be 1 by 3 of 2 lambda naught L square, 2 lambda naught L square divided by, and here I am going to get lambda naught L. So lambda naught L, and which will give me lambda naught cancels out, 1 L cancels out, so 2L by 3. And keep that result in mind. If the linear mass density is proportional to the distance from the left end, which means we have a function of this kind, then the distance of the center of mass from the left end will be 2L by 3. So the center of mass will be towards the right hand side. It will be 1/3 of the length from the right hand side, signifying that the right hand side of the rod is heavier and the left hand side of the rod is not so heavy. So that is the center of mass. Now let's take the rod of second kind, and of course this is a very arbitrary shape. We will not be able to do it unless we know this black outlines equation and its rotation in 3 dimensions to get a solid shape. We will be in trouble. So we are not going to do this. We are going to take a much easier shape, something that we can deal with. So we will take a rod of uniformly varying radius. And the radius on the left hand side is perhaps a, small a. The radius on the right hand side is small b. Small b is greater than small a. The length of this rod between the two extremes, the left extreme and the right extreme, is L. So the distance from here to there is L. And we need to find out the center of mass of this rod under the conditions that its density is uniform. So it's made up of the same material, it's a homogeneous rod, but its thickness keeps on changing. So now how are we going to figure out the center of mass of this rod? Now we know that because it is of uniform density, the center of mass must lie on an axis of symmetry, and the center line that I have drawn here is an axis of symmetry. So the center line should have the center of mass somewhere, but where? And that's why if I take this center line as the x-axis, I know that the center of mass will have only x coordinate, will have no y coordinate, will have no z coordinate. So let's not worry about the y coordinate and the z coordinate. What we can do for this problem is we can break this entire structure up into disks of increasing radii, and for each disk we can try to figure out what exactly is its mass and where the center of mass of the particular disk is, and then we can go through with the entire calculation. So what is it that we are going to do? Take some distance from the left hand side, let's say x. So at a distance x from the left hand side, let me take a very thin disk, and the thin disk may look like this. This thin disk will have a radius small r. The radius is small r, and I need to figure out this small r in terms of x. And it's a very simple thing actually. We can do this in a very elaborate fashion by taking similar triangles and everything, but I think you will be easily able to follow if I just write that this radius will be original value, the initial value, that's a, plus the total change. So from the left hand side to the right hand side, the change is b minus a, and divided by L, that gives me the rate of change. Rate of change multiplied by the distance at which I am looking at, x, gives me the total change. So the final value is initial value plus change, where to find out the change I have taken the rate of change and multiplied it by the amount of distance that I am interested in. This is the radius at this place. Now I need to figure out what is the mass of this disk. That's dm for me, right? So dm, the small mass of this disk will be pi r square, that's its area of cross section, times its length. Its length is a very small distance dx, that is its thickness. So the total volume will be pi r square times dx, and times rho will give you its mass. So this is the mass of this disk, this particular disk. And where is the center of mass of this entire disk? The center of mass of this disk will be right at the center here. That is at a distance x from the left end. So now what I can do is I can replace this entire disk with a particle of the same mass placed at this green point. And then I will have infinite number of particles placed along the x-axis. And then I know how to find out their center of mass. So the center of mass of that infinite particle system, where each particle will have this mass and its x coordinate will be x, can be found out. I can find out that center of mass by saying here on the right hand side that the x center of mass will be integral of x dm divided by integral of dm, and I just have to integrate this term. So what about the numerator then? Let me do the calculation for numerator on the left hand side. The numerator, okay, it's not n power r. So there is a case, I was doing this the last year and some student was like, sir, what is that n power r? So this is numerator, people. Numerator will be integral of x times dm is pi r square dx into rho. In fact, I don't have to do all that also. Let me simplify a bit because I know that a lot of terms will cancel out. So when I try to write the numerator on the right hand side here, I'm going to get x times pi r square dx times rho, and integral of all that divided by integral of pi r square dx into rho. And in both these integrals, pi is a constant, will be taken out and can be cancelled out, so pi, and the same can be done with rho. So I don't have to write those terms again and again. Now I only have to calculate what is x into r square dx and r square dx and their integrals. So therefore r square will be a square plus b minus a by L whole square times x square plus 2a into b minus a divided by L times x. And so therefore x r square will become a square x plus b minus a by L whole square x cube plus 2a into b minus a by L into x square. And now the numerator will become integral of x r square dx. That is what the numerator is, x r square dx. So I can do that in one step. I just have to integrate this. So it will be a square x square by 2 plus b minus a by L whole square x power 4 by 4 plus 2a into b minus a by L into x cube by 3, and the limits will go from the least value of x, which is if I take the element at the leftmost cross section where x is 0, and the largest value of x will be when I take the element at the rightmost cross section will be which will be x is equal to L, big L. So 0 to L. I don't have to worry about the lower limit, only the upper limit, and I get the numerator as a square L square by 2 plus b minus a whole square L square by 4 plus 2a into b minus a times L square by 3. And what about the denominator? So the calculation for the denominator is also very simple. Denominator will be simply integral of r square dx. So here I have got r square dx. So when I integrate this, I'm going to get a square x. The first term will give me a square x, plus the second term will give me x cube by 3. So b minus a by L whole square into x cube by 3, plus the third term is going to give me 2a into b minus a by L into x square by 2. So maybe I can throw away that 2 part. So a into b minus a by L, a into b minus a by L times x square, and the limits are still going to be from 0 to L. When you put the limits, you will get a square L plus b minus a whole square, and you have a L square here, you will get a L cube here, so there will be L in the numerator by 3 plus a into b minus a into L. That is what you are going to get. And then the final center of mass is, so therefore x center of mass will become the numerator, this entire term divided by this entire term. So I don't have the patience to write it again now. So let me copy this guy and paste it. This is the total numerator divided by, like this, and let me take the denominator. So this is the total center of mass. This is the location of center of mass. Now, does that make sense? So again, I will have to check my formula against something which I know. And what is that which I know? Now I know that if this was a rod with no variation in the radius, then the center of mass would have been exactly at the center. So if I have got a rod where the left hand side radius is equal to the right hand side radius, it's going to be a uniform cylindrical rod like that. I know that L by 2 should be the answer. And in that case, I have to insert B is equal to A. So let me take case 1. For no variation in area of cross section, B should be equal to A. That means B minus A will become 0, and the x center of mass will be, now the moment you put B minus A 0, you will have the second term and the third term in the numerator going off, and the second term and the third term in the denominator going off. So you'll have just a square L square by 2 by a square L. A square L square by 2 divided by a square L. So you will have L by 2 as expected. So that's wonderful, because we have got a right answer. Now this figure looks like, of course I have said that this is a rod of uniformly varying radius, and it might be a rod, but it also looks like frustum of a cone. So I can probably use this figure to find out where the center of mass of a cone is. So let me take that as case 2. Of course, there is another way in which we will try to find out the center of mass of a solid cone by another integration afterwards, but we can use this result. So for a uniform solid cone, what I can do is I can say that A is 0, the radius at the left end is 0, B is non-zero and some value, and there is some length L. So this is what I can claim. And then if I insert a is equal to 0 in this entire result, so when I say a is 0, the first term is going to go to 0 in both these numerator as well as the denominator. The last term is going to become 0 because there is a in multiplication. So the only term that will be left out is the middle term, and a is 0, so you will have b square L square by 4. So then the x center of mass will be b square L square by 4 divided by this term will be b square L by 3. So there will be b square L by 3, which is going to give you, if I am not wrong, 3L by 4. So the center of mass from the left end is at 3L by 4, somewhere here. And you have to keep this result in mind, people, that for a uniform solid cone, the center of mass is at L by 4 from the base. In fact, I am using L because I thought of it as a rod, but then if you take this cone, we will call its height as h. Then the center of mass is going to be at a distance of h by 4 from the base, and this is a very interesting result. You should keep this in mind. We will again find it out using a different method, but that is for a later day. But for this particular rod, which we have used here, a non-uniform rod, we can find out the result, and we can extend that to find out the center of mass of a cone. Uniform solid cone, remember that.